This slide shows the block diagram of system controller for battery dominant power architecture with uniform voltage distribution, maximum power tracking. In this block diagram, there are basic four functions: maximum power tracking control, input voltage regulator. That these two blocks are usually work together. The other two functions is battery charge control and uniform input voltage distribution control. We call it UIVD control. This control for uniform voltage distribution always active at all times. Under normal operation or non-maximum power tracking mode, battery charge controller will always active. During this mode of operation, diode D always forwards bias and making the voltage VC follow the battery charge control, and the input or the output port of input voltage regulator have significant output impedance with respect to the output impedance of battery charge controller. In this manner, during the time that diode D forwards bias, primary system control voltage always dominated by battery charge controller. As soon as the battery charge controller fails to regulate its charging current IBAT to the target, or fail to able to accommodate the V bus or battery voltage to the target, it will cause the diode D to reverse bias. That remove this part from engaging to the voltage VC. The primary control signal VC then is dominated by the input voltage regulator that working together with the maximum power tracking control. In this manner, during the maximum power tracking mode, these two control blocks, MPT control and input voltage regulator, works together. V1 considered as the total serial input voltage. That is the summation of all sourcing voltage. In this case, the sourcing voltage across power source number 1, power source number 2, and power source number 3, adding together form the total serial voltage feed to the input voltage regulator, and at the same time feeding to the MPT control. The other side of the MPT control also feed by sourcing bus current I bus that represent power signal. The output of MPT controller generates the set point voltage candidate VSP, which is corresponding to the peak power voltage candidate. Superimposed on this voltage is the AC digital signal, which is small signal of low frequency such as 20 Hz or 200 Hz. The next signal becomes the commander VSPT that contain this ripple, and as a result, the serial sourcing voltage are actively regulated to VSPT, also contain the same ripple content or have the same phase shift of the digital signal. Uniform voltage distribution provide a minor correction to the system primary control signal VC and distribute control signal VC1, VC2, VC3 that has a minor control correction in such a way that the voltage that detect across each power source V1 minus V2, V2 minus V3, and V3, these quantities are uniformly distributed or equal. This slide shows another power architecture referred to as bus regulated power architecture with uniform voltage distribution maximum power tracking control. In this particular architecture, the same simple converters, the same set of power source are connected in the same configuration. The battery, the system battery load also remain the same. The only thing that add into this system is the regulated bus called bus out. This bus out is the regulated bus that regulates firmly to a designated target level, for example 110 volts. There are certain types of load family we call bus load that require its input voltage to be strictly regulated. In this manner, in some application, bus regulate voltage become necessary to produce the reliable common voltage to feed the payload for satellite application. In order to have the bus voltage regulate, the force converter, the output isolate DC converter, generate the output voltage VO4, which is only small portion as compared to the total serial input voltage V1. Superimpose this small portion output voltage VO4 on the total system serial input voltage, produce the regulated bus voltage bus out. In this manner, the power conversion efficiency from the total sourcing voltage to the bus out can be significantly high, simply because the only power loss in the output isolated converter only provide small power to this contribute into the sourcing power to the bus out and the bus load. The DC converter can have very simple efficiency such as 85%, but the power conversion from the total sourcing voltage to the bus out can be as high as 95%, depending on the amount of the voltage VO4. The smaller the VO4 with respect to the total sourcing V1 voltage, the better power conversion efficiency. iBus still used as a way to detect the power, and iBus still using in the same manner to regulate the battery. The system controller mostly identical, only additional feedback variable called bus out, so that the control voltage VC4 can be used to control the force converter to regulate the bus out voltage.